All right. So today we'll start the last major topic for the course, which is machine learning. We'll be looking at Naïve specifically this lecture, and there's more to follow. So up to now you've seen how to use models to make decisions, right? So you've seen how to build a base net or sort of influence diagrams and then make decisions based on utility from that. In machine learning, we'll see how to actually, where those models come from, right? So you can always construct models by hand by making a base net, by filling out probabilities in those tables and so forth. But especially for large models, we really want to find we want to have automated techniques for starting from data and constructing the models. So that's what we're going to talk about starting today. And there are kind of three sorts of things you could imagine learning. You could imagine sort of having something like a base net or some other structure and learning continuous parameters like probabilities. You could imagine trying to learn structure, so you might get a whole lot of data which has got a bunch of different features, and you want to try and learn the base net that best describes that kind of factored data. Or you might want to learn kind of hidden concepts. So this is sort of, this comes up in a lot of different places. For example, Google News classifies news stories into individual news stories into clusters, into categories of news stories to show it. The way you can make money off the internet is to classify people and to figure out what ads they like and do all that sort of stuff. So it's pretty central. So today we're going to look at model-based classification with naive Bayes. And we're going to start by saying, okay, what is this classification? How can it be model-based? And what is naive Bayes? So classification in general is, so here's our canonical example. You're given an email in your inbox, and you want to figure out, is that spam or is it ham? Is it a good email that you want to see, or is it something you don't want to see? And so that's classifying the email into two kinds, spam and not spam or ham. So what this looks like in more detail is you're given some kind of input, so you're given email as an input, and then you want to output this binary label, spam or ham. And so the setup is you're going to have a large number of example emails generally. So you're always going to have some pool of data to train from, some corpus. And so you'll have a large collection of emails, label either spam or ham, and you're going to learn from that. So someone's going to have to hand label this in some fashion. So someone will have to do this. And that someone is probably you. Or you can get we'll go into how that could happen. You could use Amazon Mechanical Turk or something to do it, or make a game where people incidentally classify things for you. So there's a lot of work in that. So here are some examples. So, okay, I guess I skipped ahead. So, dear sir, first I must solicit your confidence in this transaction. This is by virtue of its nature as being utterly confidential and top secret. Spam or ham? It's probably spam. Okay, and there we go. And so the second one, okay, this is looking pretty spammy too. It's in all capitals, 99 million email addresses. But maybe it's not. Maybe you're actually really interested in buying email addresses, and so for you, that's not actually spam. So this gets into a sales question of spam and ham depends on the person. And this one is probably okay, but it would look suspicious, right? So there are some words that are kind of misspelled here, or kind of joined on together. So
it may actually be motivation for believing it's not spam. Spam is probably not going to have a lot of misspelled words.
Spam tends to have a lot of a lot of spam does have misspelled words, but part of the reason they probably have misspelled words is people misspell words in practice. So they're trying to match the empirical statistics of people who write emails. And then people are not perfect spellers in the wild. So the kinds of features we might look at is, there are particular kinds of words that often occur in spam, like you're going to get something for free. There are certain kinds of patterns. You could try and tell whether the sender is in your contacts or not. If it's in your contacts, it's probably not spam. So generally speaking, so we've got this general setup is we've got some input we're trying to classify into some categories, and we've got a whole bunch of data on it, and then we've got features of that input. So we're not just we've got to find some way to kind of summarize and extract properties or features of the inputs. And that will, most of the effort in machine learning turns out to be engineering features and iteratively figuring out which features are the good features. So another example is digit recognition. We'll look at it as a computer vision problem. Pretty useful commercially. So you're given images, so they've got like a pixel array as your input, and you want to figure out is it 0 through 9. So again, you're going to have a whole lot of labeled data, and someone will have to do that. And you want to predict the labels of future data given what you know from the past. So you can imagine features for this. The easiest features would be like, is a pixel on or off? Or it could be like some pattern of the shape. Is there, how many loops are there? Are there circles? Are there lines? How many connect components? Anything we could imagine writing a program to compute from the input, we could use as a feature. And so this one, okay, that looks like a 0. The next one is maybe a 1 or a 7. This one's probably a 2. 1. Who knows? I mean, this one, it looks kind of like a 0 or back to front 6, or it's probably a 0, but we don't really. You get these ambiguous cases. Or it could be a 2, right? It looks like maybe an incomplete 2. So there are lots of, I mean, this is a huge area. There are lots of different other kinds of classifications. So there's the spam, there's like the OCR, reading digits or letters. There's medical diagnosis, there's automatic essay grading. You don't think your professors read all your essays, unfortunately. There's fraud detection. This is what made online credit cards actually feasible, is you could automatically detect whether something was fraudulent or not, or that was what was needed for like PayPal to work. Customer service email routing. So all these different things are basically, you've got some kind of input coming in and you want to figure out, you have some set of kinds that you want to sort the inputs into. Right? So it's a very general kind of thing. So what is model-based classification? So there are a number of ways we can classify. In the next lecture, you'll see kind of things that are not really directly model-based, but what is a model-based approach? So you build some kind of model. In this case, it's going to be a base net, which where the label and the features are both random variables. So you've got a base net with various features, and then the labels coming out the other end. And what you do is when you're given an input, you compute all those features, you condition on the values of those features, and then you compute the label from the other end. So you do kind of base net inference. And so there are two main questions here. What structure do we want this base net to have? So we're going to assume a fixed structure. Given that structure, how do you actually do inference on it efficiently? And then what should the models look like? What should the parameters look like? And how can we learn them? So we're gonna address those in turn. Is there any questions so far about the basic setup of what we're trying to do? Okay. So in Naïve base, we assume this base net on the right here. So we have all the features. So Y is the label. So that's going to be, say, spam or ham, or the particular category of the digit. And then condition on the label, we generate independently all the features. So this is the critical assumption which makes the model both tractable to specify and to do inference, is that given that you know what kind of thing it is, all the features are generated completely independently. So for the digit recognition, we'd have, say, one feature for each grid position, and then it's either, say, on or off, and then once we're given an input like this, you can then map it to this feature vector. Whoa, okay. And so that's a vector of numbers that we can learn things from, and each of them a binary value here. And in Naïve base, we're assuming that this factorization holds, right? So the probability of y given all the features is proportional to the probability of y times all these independent products. And the reason we have a proportionality constant here is you would get exact equality if you divided by, let's see if I can write this, the probability of the features, right? So if you could divide through by that, that would be exactly correct by the conditional probability definition. But we don't actually need to do that. That's more work than we need to do because we only care about the relative probabilities of y. So we can just compute these for each possible category and then normalize, and that will get us the distribution we want. Yeah?
This then is essentially identical to the previous integration between we've seen, where you have a list of features corresponding to a certain state, and those features will tell you what the value of the state is.
So you mean like it's a linear function approximation for like Q-line? It's similar. It's a kind of a probabilistic version of that. Yeah, there are connections between the two. It's not equivalent, no, but it's related. It's a similar kind of idea. Goes into feature engineering, right? Trying to figure out what are actually appropriate features. Any other questions? Okay. So what do we need to learn? So in general, I guess let's treat this generally. So in general, we're going to have to learn this probability here. So we're going to have a prior probability for each of the different categories. We're going to have some prior probability of each of those. So what is the probability that a random email is spam or ham? So that sort of sets things initially. And then we're going to have these conditional probability distributions for each of the different features. What is this conditional distribution given the category, right? And that's just, if this is your base net, that's just all you need to specify that base net. So it's pretty straightforward to make such a model. And so overall, there are going to be, so it's the total number of values you get, right, when you compute out all the different joint probabilities of label and features. So it's going to be the number of possible categories times the total number of possible feature values. So if we assume that each feature is valued in the same set. But we only need a smaller amount of data. So we only need this here. We really need y parameters, or really y minus 1 parameters, because they have to sum to 1. And then we need for each possible, so I guess n is the number of features. So for each feature, we need to have its conditional probability table. So that plus that is much smaller than that. So it's a very compact way to specify a model, especially if n is 1,000, you have thousands of features. So it's linear in n is really the main thing. So you can add a feature with a linear cost. So this is kind of simplistic. It's sort of crazy given the features. So if you imagine, okay, how would you draw a 2? If you've decided to draw a 2, you want to generate a picture from that. You're probably not going to look at each pixel independently and then randomly decide whether it's on or off, right? How you would actually draw it is you have a pen and you draw some kind of stroke. And depending on where you start, it's going to affect where you finish. Like there are all these correlations within the features. But there are kind of two things here. One is that with more complicated features, that's less true. So you can choose features that are more independent. But secondly, you can just ignore that fact, and it still works. So even if you're not modeling all the correlations, you could still be gaining enough information in order to do classification well. So this is sort of a case where the model is not the most accurate model you could imagine trying to create, but the model is kind of good enough. Yeah?
How'd you go from the number of values on the left to the number of values on the right?
So the number of values on the left is this one here. So this is just, you imagine all possible joint assignments. So you're going to choose something for y and you're going to choose something for all the features. And so this is the total number of ways of doing that. And then this is just the number of parameters you need for the base net. Yeah. Okay, and so inference for this is really a special case for inference and base nets. It's pretty simple. So what we want to compute is we want to compute this joint probability. We're going to normalize it. And then that's a big vector for each possible value of the classification, the probability of the instance having that category and having all the features it has. And so that is just equal by the product rule and by the definition of the base nets. That's just equal to this product. So you start with the prior probability and you multiply in for each feature value the conditional probability of that feature given that category. So this is called the likelihood of that feature given the category. And so that's just a bunch of multiplications. And then you can, if you sum these up, you'll get the probability of, just the probability of seeing an instance with those features, and you divide through and you get the probabilities you want. So you get this. So that's exactly how inference works. It's very simple. Sort of, you can imagine like a 4-line algorithm for doing this or something. So is that clear? How if we're given a model, how we would do inference in the naive Bayes case? Is that clear, or are there questions? Yeah. Yeah, that's the assumption. That's exactly the naive Bayes assumption. Yeah. Great. Okay. So what do we need to use in order to use naive Bayes? So first we need to be able to do inference. So we've just seen that. And then we need to have these local the conditional probability tables, right? So we need to have this prior probability here. We need to figure out what that is. We need to figure out what the probability of each feature is given the categories. And together we call these the parameters, and that's traditionally noted by theta. And so we've assumed these are just magically created, but we're going to show soon how you could actually compute them, and different ways of computing them from data, some which are better than others. So just to get a picture, get some intuition, what would these things for the digit classification example, what would good probabilities look like? So we're going to start with some prior so there's going to be the probability for for 1 through 0, all the possible different digits. We might assume a reasonable prior is to say they're all equally likely. So that's not actually true, and statistically, if you a random digit, it's more common to have a smaller value. But if you've got enough evidence, it doesn't really matter if your prior is not as accurate as it could be. And so then for each feature, so if we have the features being the pixel values, then we need to have these tables here, right? So the probability that the feature is on, given each of the possible categories, and that's going to be some distribution here. So that all sums, that doesn't sum to 1, rather. That is, once you fix the category, this is the probability of it being on, and the probability of it being off is 0.99. So each of these values is a binary distribution over 2 possible outcomes. And so I guess if we look at this, so this sort of seems plausible, like for 4, 5, and 6, and 8, you could all imagine, if you imagine drawing the shape on it, that this square should probably be on. And also for 0. And for these other numbers, it should probably be off. And so if we look at this square here, we have a similar kind of thing, but it's just different. So for 3, say, it's pretty likely it's going to be on, and indeed it's on. And for, you can kind of look through all these things. So one way you could imagine computing all these numbers is you collect a whole bunch of different images, right? And you look at all the 3s, and then you count within, let's say you have 1,000 different 3s, you count in what proportion of those images is this square on for a 3, and then you divide through by the total number of images. So that's the easiest way you could imagine setting this. And we'll see that yields some problems. We'll get better ways in a moment, but just to get some picture of where these numbers could come from, that's one way. So this makes sense for the digits. So for the text example, so the spam and ham example, a common model is called the bag of words model. So basically what this is, so the intuition is that we're only going to care about which words occur in your email or in your text and how many times they occur. And we're going to completely ignore where the words occur and in what kind of order they occur. So the features will be, for each position, the probability, the word that occurs in that position, right? So this could have maybe 100,000 possible different values, right? Any word you can imagine in the dictionary is going to be one of those possible values. And so we're going to do, so everything will be the same as before, except we'll make this critical assumption that the distribution for each word is completely independent of where in the text it is. So the probability that the first word is the is going to be exactly the same as the probability that the second word is the. So that's a simplification. That's really in order to minimize how much data we need to have in order for this to work. But it's not too bad a simplification. And so this is the generative model. As before, in this case, we only have one conditional probability table there. And note, this is, the WI means the word at position I, not the ith word in the dictionary. So you can imagine a different representation where, say, your feature was the number of times a particular word occurred in the text. So the number of times occurred in the text, the number of times money occurred in the text, right? So that's a different way of doing it. So, yeah, so that's what I've said so far. So it's this, another way of calling, another name these are called is tied distributions, because you imagine they're kind of tied together. They're tied to be the same. And so as an example, so Dan Klein, or one of his students, actually computed the Naïve Bayes model for spam filtering. They had a whole bunch of spam and a bunch of ham, and they computed these frequencies. And so it turns out in this case that, okay, there were 66% of them were ham, were good emails, and 33% weren't. And this is the distribution of the words in spam, right? So the most common word is the. So that's something you would expect. That doesn't really tell you, none of these really tell you anything about the most common words in spam are probably going to be the same as the most common words in ham, just because it's the same language, right? And so there are these small differences here. There's this, I don't know, maybe ham is more likely to say the current year or something. You could try and make up a story for why this is true, but if you start looking down the end here, there's going to be maybe it's like 100,000 different entries here. Down the bottom, you'll start to see words that are more characteristic of spam, like free, money, strangely shaped words. So if we have these, so we imagine using these tables, which extend out to a large amount, we'll run through, just to sort of really solidify how this algorithm works, we'll run through one particular example. So you can imagine when you're given an email, basically what you're going to do is you're going to compute a probability. You're going to start with sort of the prior probability, and then for each feature, each word you'll go along in turn. That feature will get you a new probability that you'll multiply in, and then you'll repeat, right? So in this here, you imagine starting with a vector of all the probabilities of y's, and then this is a loop. You loop over I, and then you multiply in these terms one by one. And to simplify this, what we usually do is we use log space. So we take the log of all the probabilities, because that means the multiplication, when you're multiplying, you're just adding logs. And so that has two benefits. it's sort of, well, one is more intuitive, and it avoids like underflow. So you imagine multiplying a lot of probabilities, they're very quickly going to go all the way to 0. So that's what's typically done. And so let's leave that. Okay, so the first word is Gary, and apparently Gary is 10 times more likely to occur in ham. So maybe the emails, this is taken from Gary's email or something. And so there's a 0.0002 probability of that word occurring if it's ham, and a 0.00002 if it's spam, right? And so what that happens is if you take the log of this and you add that to this, so that's going to be, apparently log of this is about minus 10.7, and then you do the same thing here. The log of this, you add it to that number and you get minus 8.9. So here's another word. Apparently wood is slightly more likely to occur in ham. So this, we add on that log probability. U is apparently 2 or almost 3 times more likely to occur in spam. Maybe spam is always telling you are going to get something, but that's less likely in ham. And then you continue out, right? So you've got all these sum, and notice they're always decreasing and they're always negative, right? So that's because probabilities are less than 1, and so log of anything less than 1 is negative. And so at the end of this, you see that this is the log probability of it being spam, and this is the log probability of it being ham. So what do you think it is? What's it most likely to be? Is it spam or is it not? It's spam, right? Because this number is bigger than that number because it's negative. And it's in fact very likely to be, like the difference here is, it's 4, but that when you take the exponential of that, it's like e to the 4 times more likely. So that's quite a large number. And often you find in these, one of the negative effects of the independence assumption is you assume you've got more evidence than you really do. So often, out the end of this, you get these really extreme probabilities. But as long as the difference is in the right direction, it's not too bad. So does this algorithm make sense? This is the Naïve Bayes inference algorithm. Cool. I guess that's what it works out to be. 0.98 probability. Okay, yeah. So this is, okay, let me see if I can draw with this mouse thing. So this is equal to, if you take the exponential of both of these, the exponential of this will get you the probability that it's spam, that you get a word that is spam and it has an email that is spam and has all those words, so the joint probability. If you take the exponential of this one here, you'll get the probability that it's ham and all those words occur. So if you take the exponential of these two, you're going to get 2 numbers. And then you divide through by their sum to normalize it, and that's where this will come from. So this is going to be something like e, so spam is this one, e to the negative 76. Ooh. Divided by, I wish I had Peter's computer. Okay, e to the negative 76 plus e to the negative 80.5. Does that make sense? Yeah. Any other questions? That's good. Yeah.
Is there a reason why U shows up twice in the table?
That's because it occurred twice in the email, and so we count it twice. So we count each word. This is the feature. This is sort of feature 1, and this is feature 2, feature 3. And remember, the features were the word at that position in the email. And so if the word occurs twice, we want to count it twice. Yeah.
Is there anything wrong with just adding the probabilities, or does that take the log of it?
Basically, it computes the wrong thing, I guess is the general answer. Like, let's see how this works. So if you're adding probabilities, so for one, I mean, if you're adding these kinds of probabilities, you're going to quickly get numbers that are bigger than 1. So you're going to get things that are not probabilities at the end. These are, so let's say you added, let's say you had enough words, right? Maybe you had 10 you had 100 twos in your email, right? Which could happen, right? You could be some span could be like 2, 2, 2, 2, 2, 2, 2. Then if you're adding probabilities, you would get like a probability of 1.3, and that's not a probability. So it's basically coming down to the reason we're adding them, the reason we're multiplying them is multiplying probabilities is we want to do this equation. That's the probability. If you look at the BaseNet stuff, that's how the correct way of computing the BaseNet probability is we multiply, we don't add.
So even though this is a product of, you can just take a log of that.
Yeah, so if you take a log of this, right, so you know that if you take, so the log of this here is going to be like log of probability of y. I don't know why I'm trying to write these things. That's going to be, so right, plus, because when you take the log of the product, it becomes a sum. So you're going to have like a sum of log of probability wi given y, right? So that's where the algorithm came from, is that if we take the log of this product, we're going to get the sum of these logs. So, yeah. Any other questions? Yeah. That's a typo. It should really be like 98.9%. Yeah. Anything else? Yeah, exactly. Exactly. That's what it should be. Cool. So this is a good place to have the break. So let's do that. All right. Let's continue. So before getting into how to train the naive Bayes model in particular, we'll discuss a bit about like some general concepts of how training and testing works in machine learning. Right. So this is much more general than naive Bayes. And so basically there are 3 phases. There's the training phase, right, which is most of your data is going to go to training all the different parameters in the model. So that's where you would assign all the probabilities. You tend to have, then you have basically a practice exam on a separate set of data where you might have a couple of additional parameters that you want to vary based on its performance on the practice exam. And then the final exam is when you really get to see, okay, how good is your algorithm? And that's the number you put in your data. So how does that work? So you have, you've got a whole lot of data, and you're going to divide it into 3 parts. So you're going to divide it, most of it is going to be the training data. You have a little bit of held out data, and you're going to have finally a little bit of test data. So why do we split it into these parts like this? Why do we will split it kind of completely randomly? The basic reason is that we want to use them for different purposes. So typically our model will have, say, a large number of parameters, like in the BaseNet there's a huge number of probabilities. We want to have one data set on which we just use that to figure out what those probabilities are. We might have then some additional parameters, like we have, later on we'll see one example of this, but you could imagine in a more general case, let's say you had 2 different kinds of models you wanted to compare. Like you had 2 different BaseNet structures, and you want to figure out which one of the 2 is better. So you can use the held-out data to choose which one of your 2 models is better, without without cheating, right? If you could actually use the test data, the critical thing you want is you want to create a model that's going to that uses as much of the training data as possible, so it generalizes, and it doesn't overfit. So you're not like, if you could imagine if you're really learning the model correctly, you're not just learning to the test, basically. So sort of, if you're given the final exam, you could just figure out what all those answers are, and you haven't really learned the general concepts behind it. And it's the same thing in machine learning. So that's why we split it into these 3 bits. And so the general measure of accuracy is, how often do we predict things correctly? And yeah, so this is what I was saying before. We want to avoid overfitting, and we want to gain generalization. So just as an example, so you've seen this before, I think, with the reinforcement learning, but we'll look at it again. There are 2 kinds of errors you could do. You could imagine underfitting your data, so your hat is too small. So you don't actually use the data, right? The easiest way to do that would be you throw out all your data and just create a model that has got uniform probabilities. That is certainly not overfit to the training data, the training set, but you haven't used the information you've got to its full potential. So the opposite error is that you fit exactly to the training set. So you predict precisely everything you've seen before, but in trying to match exactly all those things without any errors, you then assume the whole world looks exactly like that training set. So you make the opposite error. So you want to have something in between these 2 extremes. So what's an example of overfitting? You imagine having a data point like this, and probably a good curve is something that looks like this, right? It's not going to be exactly correct on all of these data. It's not trying to match all those points exactly, but it looks like it has the overall kind of trend. Something like this is a very bad curve, right? So it looks pretty good on the training set. Like if you only see these points here, okay, it's looking pretty precise. There's a little gap on a couple of these 2, but it's on the test set, on the training set rather, this would have a very high accuracy. But if you can imagine what the test set would be, it would be basically the value of the function at these other points here. And so that's clearly extremely wrong there and extremely wrong here. Like in trying to get exactly correct for these 2, it's just completely messed up elsewhere. So that's what you want your your learning models not to do. And so the underfitting in this case would be something like you just assume that it's all 0, right? You don't even look at the numbers, and you haven't really learned anything at all. So we'll see a bit later how you can deal with overfitting. One of the ways is to use this held out set. So what does this look like in our running example of the digit classification? So let's say we're given this is our image, right? So what number do you think this is? It's 3. That's probably a pretty good guess. All right, what does Naïve Bayes think it is? So Naïve Bayes looks at the prior probability of it being, so is it a 3 or is it a 2? So Naïve Bayes thinks, okay, those are initially equally likely, but hasn't seen any of the data. So it looks at this pixel value here. So this is about equally likely to, this is exactly equally likely to be on for either a 2 or a 3. So just looking at that pixel doesn't tell you anything. We look at this next pixel, and that's pretty likely to be on for a 3 and pretty unlikely for a 2, right? Because 2 is going to kind of go down here. This point here is also the same thing. So up to this stage, Naïve Bayes is going to think that it's a 3 and it's probably not a 2. But then if we look at this pixel here, this spurious pixel, it so happens that there's a very small probability of a 2 having a pixel there, but a completely 0 probability of the 3 having there. So if you multiply all these together, you get 0. And if you multiply all those together, you get something bigger than 0. So it's probably a 2. So that's pretty insane. And that's an example of overfitting. So how might this happen? You could imagine that it just so happened that one of the 2s looked kind of crazy. It looks sort of like, I mean, that's a pretty reasonable 2, right? We got a 2 kind of like this. But none of the 3s have a dot there, because that's just like a piece of noise. And so if you just use the counts on your training data, you will predict a 0 to something you've never seen before, which is overfitting. That's wrong. So the canonical example of overfitting is assuming you'll never see something you haven't seen already. So this is a 2. Okay, that's not so smart. So what does this look like in the word case, in the like email case? So really what matters is the relative probabilities, right? So the absolute probability doesn't matter because in the end you're going to divide through by the sum. So if this was 0.1 and this was 0.1, it would still have the same effect because all the numbers both numbers, probabilities would decrease by the same ratio. So really it's just these odd rate, they're called odd ratios that matter. And so, okay, what's the top list for hams? We get odd ratios of infinities. So if your email has the word Southwest, it is infinitely more likely to be a good email than spam. No spam ever has the word Southwest. And no spam ever has the word nicely or seriously, like a seriously good deal. That's pretty dumb. And then a similar thing here. If you have the word screens, you're definitely a spam. Or if you had the word minutes, like let's meet in 20 minutes. And all of this happens because the particular way this thing was learned is it only looked at the frequency in the training data, and if it never occurred, then you thought the probability was 0, right? So these infinities are coming because you're dividing a positive number by 0. So, not good. So, these relative frequencies, these probabilities where we estimate the number of times it occurs in the training data will always overfit, right? And so we've seen that. So we want to have some way of dealing with words we've never seen before, or just things just random stuff that could happen, right? And we basically never ever want to assign 0 probability to anything ever. That's kind of, if you take one thing from probability, don't assign probability 0. It's infinitely bad. And you can imagine, like, if we just had the entire email as the feature, then we wouldn't generalize at all, right? We'd be like, so if we had these features, we could create a model that would predict the training set exactly correctly, right? Because it could just remember for each email what its classification was. But when it gets a new email, it's going to be like, have I seen this before? No, I don't know anything, right? So we need to have some way to, basically, to eliminate these 0 probabilities, we need to smooth or regularize is the term. And so we'll see how to do this. So first, let's look at just parameter estimation in general. How does this work? So how are we actually learning the probabilities? So we've got we're trying to fill in a base net, right? So we're trying to estimate the distribution of a random variable. And so how could we do it? So one way is we could ask a human, right? And what is the probability that obviously occurs in ham versus spam? Probably you don't know, right? I have no clue. So that's one of the problems with that is, okay, humans often don't know probabilities. And 2, you probably get tired when if I go through the whole dictionary and ask you the probability of all these things, right? So humans are limited in that way. So we want to somehow use the training data, which is this is machine learning, right? That's what we're doing. And so far we've been looking at just counting the frequency that occurs in the training data, inside the training data, and assigning that as your probability, right? So here we would say, okay, what is the probability of red? Well, there are, so this will be our estimate. We count the number of times it occurs, and we divide it by the total number of samples. So the probability of red is going to be 2/3, right? So that's what you've seen. That's the straightforward thing to do. So where does this come from mathematically, right? So if we're trying to think of ways to do something less dumb, we want to look at why would anyone want to do this in the first place? So it turns out that this ML stands for maximum likelihood. So what using the relative frequencies maximizes the likelihood of the data given the parameter. So what is that? So the likelihood, which is just this quantity, here, that is just the if you think for a little bit, what this is this is just the probability of the data given your model's parameters. Because these are really conditional probabilities. It's the conditional probability of some particular email having a particular, some data, right? So some email having a particular category given that classification. So in this case, what the likelihood function looks like is, so you've got, so the theta here is, say, the probability of red, right? And you want to figure out what that is. So if you knew what the probability of red was, with what probability would you estimate seeing, red, red, blue? Well, red occurs with probability theta, by definition. Red occurs twice, so that's theta squared, and then blue occurs once, and that's got probability 1 minus theta. So that's the likelihood function. And then maximum likelihood just picks the value of theta, which maximizes this expression. So if you figure out, with the caveat that theta has to be between 0 and 1 because it's a probability, right? So if you look at this, you might realize that, okay, if I take theta to be negative 1,000,000, this is going to be really big, right? But that's not what you want to do. So if you do the math here and you take the derivative and set it to 0, and then figure out which one is, take the second derivative to figure out which one is the maximum, this will come out as this ratio here, right? And in general, it's a worthwhile exercise trying this out. If you have theta to the x times 1 minus theta to the y, the maximum of that is going to be at x divided by x plus y. That's a good exercise for your understanding. So that's where that came from. So maybe we can do something better. So, okay, so it turns out that these counts are maximum likelihood estimates. So just the one reason why that you've actually learned something interesting there is that you can have other kinds of models where it's not clear that counts are the right thing to do, right? So likely you can always compute, if you've given a probabilistic model, you can always compute the likelihood of the data, because that's just what a probabilistic model is made out to do. And in some cases, maximizing that will correspond to computing these counts. But there are different things. So, for example, let's say your model was a normal distribution, right? So a bell curve, which has a mean and a variance. If you figure out what the maximum likelihood normal distribution is just going to be the sample mean and the sample variance. So the sample mean is like a count, but the variance is not really, it's not quite the same thing. It's sort of related. But, so maximum likelihood is more general than just this idea of counting relative frequencies. But there is another way of doing this, which is basically, rather than trying to find out what is the most likely assignment, you could try and compute this thing, right? So you'd be, okay, let's do a Bayesian thing. So in probability theory, you want to condition on what you know and try and figure out the distribution over what you don't. So you know the data. You should condition on the data and figure out, given the data, what is the most likely model parameters. And so that works out to be just this by definition of, Bayes rule. And you can throw away this denominator, because if you're just trying to find the maximum value of this expression, this is a constant, and it's a positive constant, so it doesn't change which one is the maximum. So this is a different way you can do these things, where basically what you're doing is you're saying, maybe we know something we already know something about the prior. So if you imagine we assign the prior probability as just uniform. So if the prior probability of a parameter is just 1, then this is the same as that, right? This will just disappear. But we can try different possibilities and see which ones work better. So there's a rule called Laplace's law of accession we're going to get into. Just to correct the historical record at this point, people usually say that he was trying to figure out the probability that the sun rises, and he didn't really know very much about how suns work, so he decided, okay, I'll count how many times the sun has risen, and then I'll use that as the estimate of the probability that the sun will rise. And it's kind of a weird thing to do, you know. I will start counting today, okay, the sun rose today, so the probability of the sun rising is going to be, like maybe 2/3 or something. So it turns out that actually Laplace basically invented Bayesian probability theory. So Thomas Bayes kind of did a special case, Laplace did the full treatment, and his opponents made fun of him with this. He had a little toy example somewhere in the middle of his big book, and then this is what he's remembered for centuries later, is his little silly toy example as somehow being philosophically important. But, so, just to set the record straight. So what did he do? What did he propose? So there are good probabilistic reasons for this, which we can't get into here, but if you're interested in probability and where this comes from, see 281A. The idea is we want to eliminate the probability. We want to make sure we'll never assign zeros to anything, right? Because zeros are wrong. So if we were just to, one way would be to ground this is basically, let's assume initially we're seeing everything that could occur exactly once. So we're going to, rather than counting things starting from 0, we're going to count things starting from 1. So you imagine you've got one red here. Oh, that's, assume those are circles. Okay, and one blue here. So we're going to start with this initial thing. And so you can see that if you do that, there's no way you're going to get 0, right? Because you've always got at least one of any possibility. So what that works out to mathematically, right, is this. This is the count of a particular outcome, and we're just going to add 1 to it. When you sum through like this, that just simplifies to this, right? Because the total number of counts simplified sums up to n by definition. And then you have a +1 for every possible outcome. So we've got a plus the number of x. So what that looks like here, so maximum likelihood would assume that the probability of red is 2 divided by 3, right? Because you've got 2 of them out of 3. And then the probability of blue is 1 over 3. So in Laplace smoothing, we add 1 to each of these. So now the probability of red is 3 over 5, and this is 2 over 5. So you can imagine that if we only had 2 red, for example, maximum likelihood would say is the probability of 1 being red. Whereas Laplace would say, 1's a little bit too extreme. It's really going to be, 3 over 4. Does that make sense of what this is algorithmically? Okay. So you could imagine just generalizing this, right? So if we want to try a variety of different ways of estimating probabilities from the training data, let's just throw in a k here. So this kind of corresponds to, if you look at the Bayesian mathematics, it corresponds to choosing different kinds of parameters. So there's some sense in there. But if you just looked at the equation, you could imagine let's just throw k in there, and rather than adding 1 of each count, let's add possibly fractional counts, possibly 2. We could try different ones and see which ones work best. And so you can see that this strictly generalizes maximum likelihood, right? So when k is 0, this is maximum likelihood. And the bigger k is, kind of, the stronger the prior is. The more, if you imagine as k goes all the way to infinity, basically we're just assuming that every possibility occurs equally often without looking at the data, right? So it's throwing away the data. But in between, there's probably some sweet spot where the probability is good. So Laplace 0 looks like this, right? Where that's just the maximum likelihood. Laplace 1 is the one we've seen before. And then Laplace 100, we add 100 reds and 100 blues. So we get 102 reds divided by 203 and 101 divided by 203. That's pretty close to half-half. If you see a lot of data, this will eventually cancel out, right? If you see 1,000 reds and then 500 blues, this is going to start to be closer to 2/3. So it's really smoothing the estimate. It's making it kind of closer to uniform. And when you're estimating conditional probabilities, right? So what we need for naive Bayes is to have these probabilities of features given the class. We just do this independently for each category. So if y is if either spam or ham, and then x is maybe the word that occurs, then our estimate of this conditional probability table is going to be the total counts of x's and y's that occur plus k divided by the counts of all of that category plus this. So this is our formula for how we estimate from the data a naive Bayes model. That plus this one here. Does that make sense what we're trying to do? Like how we compute that? Yeah. So the x in this case represents a feature. So maybe x would be in the text model, the x would be what word occurred. In the digit model, it would be, say, whether a particular pixel is on or off.
So when you multiply k times x, that would be k times the weight of that feature?
So that'd be k times the number of possible values for that feature. So in a binary feature, you'd be multiplying by 2. In the word case, it's a little bit extreme. You're going to be multiplying by like 100,000 because you've got 100,000 possible words, and you're starting them all off as ones. So maybe you don't want to start them as ones. Maybe you want to start them as some very small number.
So that is the number of features.
That's the number of, given one particular feature, it's the number of values that feature can have. So you have to have one conditional probability table for each feature.
So would the feature then be the word and then all the different words possible about it?
Yeah, that would be one example. Exactly. Yeah. For this case here. So basically what this would correspond to is, let's say, so maybe we have 2 coins, right? Or we've got like, a coin that's got red on one side and blue on the other side. And we're trying to figure out, you've got like a loaded coin. So in one case, it's much more probable that reds will occur. In the other case, it's much more probable that blues will occur. And you're trying to figure out which coin you've got. Or maybe you're trying to figure out, maybe it's a better example. One is you've got a fair coin, which is always 50-50. And you've got another one that's got more likely to be reds. So you would observe, in order to create your model, you would say, okay, if the coin is unfair, okay, I've got a whole bunch of label cases of I flipped the coin, the unfair coin, and then it came out maybe 2 reds and 1 blue. And I flip the fair coin, and maybe it comes out 2 reds and 2 blues or something. And so I would look, okay, first I look for the unfair coin. Okay, here are my counts. So X in this case is the color, and Y is whether the coin is fair or not. So these are X's here. And then maybe we choose different Y's here. And so this would be say the total number of times we flip the unfair coin, and this would be the total number of times we flip the unfair coin and red occurred. And so that's how we would divide for our frequencies. And you can see that really we're just doing this. It's sort of, once you've fixed the y, a conditional distribution is just a distribution over things. And then if we had the y for the fair coin, that would be like a different value of y. That would be y fair, and then we'd get a different ratio there. Does that make sense?
Yeah.
Anything else? Cool. All right. So we're going to skip over this in the interest of time, but basically, well, no, I'll do it briefly. So you don't need to know this, but basically, there are all these other crazy ways of trying to estimate probabilities. And one problem you have with Laplace is that if you've got a very large number of values or a very large number of classes, it doesn't work so well. So if you're trying to classify emails into, say, 1,000 different kinds of emails, you're just probably not going to have very much data for each class in order to figure out what those classes look like. So what you could do is you could say, okay, I'm going to just build a model of the probabilities. I'm going to put all my data together and forget the label and say, okay, what words occur in just English? What are the probabilities of different English word frequencies? And then I'll also learn, okay, this conditional probability of, okay, I'm looking for a word, email that's about recipes or something. Okay, look at all those ones, look at the word frequencies there, and just average between the two, right? So the closer A is to 0, the more we're going to use the prior of the words. And the closer is to 1, the reverse. So if alpha is 0, then we're just going to, we'll estimate the same thing for every category. And if alpha is 1, it's just the old thing. So there are a whole bunch of other schemes like this, but basically what you end up having is you get these, at the end of it, you get these extra free parameters you've got to figure out how to set them correctly. And you've got to choose between, okay, what kind of model do you want to do? So and there, 281A and especially 288, which is the natural language processing class that Dan teaches, we'll give a number of different ways of doing this. But the upshot is basically there's not only one way of going from data to probabilities or data to models. There are always going to be choices, and often there are going to be parameters. You've got to figure out how to fit those parameters. So I'll touch on that just after this. How do you choose the parameters? The first, here is so if we went back to the data for the spam and ham, and then we did the Laplace smoothing, and then here are the probabilities that came out at the end. And so this starts to look pretty good. So apparently, back when this was done, Helvetica is used in real emails, Verdana is used in spam. Who'd have thought? This kind of makes sense. Credit, that's probably a spam. These are all very ordinary words, and there's some crazy things. Maybe spam optionally change the font. Money, that makes sense. So these are reasonable choices, but also none of these are infinity, right? This is all just saying, okay, if it's Helvetica, it's 10 times more likely to be, or 11 times more likely to be a ham versus spam. That's not a crazy amount, right? So you happen to have an email that was in Helvetica and it said money, 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 you'll still be able to detect it correctly, right? You're not going to do anything foolish. So smoothing works. It gets better answers. So that's a well-fit model. So we had this, in the smoothing case, we had this k parameter we needed to figure out what the value was. How do we do that? So this is called tuning. So basically, we have these parameters that we fit on. So remember, we divided our data into training data, to held out data, and to test data. So we use the training data to figure out the parameters, these probabilities here. And then what we call hyperparameters. So that would be, for example, the k in our Laplace smoothing, or the alpha in that linear interpolation. Those are hyperparameters. And the way we're going to set them is basically in the following way. So you imagine this graph here. So this graph here is the accuracy of the model. You train it, so you take a model, you train it with parameter k in the Laplace smoothing, and then on the training set, and then you evaluate on each of these different 3 sets its quality. So this curve here shows that assigning k equals 0 is the best thing to do to maximize the probability of the training data. And so that makes sense because the whole idea of that k was to kind of smooth away from the data, to not try to overfit to it. So the training data the accuracy on the training data would be maximum when k is 0. But if you test it on the held out data, this green curve here, you find the maximum is actually somewhere here. So it's better to kind of smooth it because that means it's not assigning zeros to anything. It's not exactly fitting the particular emails you got. So what you would normally do is you would run your training algorithm for each value of k from 0 up to something, and then that would get you your probabilities. You would then use that model to classify all the held out data and compute the accuracy on that, and that's your green curve, and then you would maximize that. So the red curve here is then, on the test set, it might be like a slightly different value of k is better. But the reason we don't want to run on the test set is because we don't want to fit to the exam, right? We want to have something that we expect to generalize to new data that we've never seen before. So we're learning the parameters from the training data. We use different data, right, for this reason here. Here we get the overfitting. And here is underfitting, right? If we set k as to be really big, we're just going to assume everything's the same probability. And yeah, so the final test on the test data is that you only want to do that once, because otherwise you have no guarantee that it's going to generalize to new stuff. So this is how you tune, and then this is then the full cycle. So the full cycle of getting data, figuring out how to learn the model, figuring out how to set the hyperparameters. That's everything. Almost everything. But does this make sense? Okay, the almost everything was features, right? So we assumed that we're given features. And so we were having in the email case, the features were just the words at each position. And in the digit case, we had the words as the pixel values. So how would you get new features? So a really common way to do this is as error analysis. So we run the algorithm with our given feature set, and we look at what classifications it makes, and we try to find ones where it does dumb things, where it makes mistakes. So these are some mistakes here. So let's suppose that this is probably, this is quite plausibly a ham message. Like maybe you are a global scape customer, and you really want to know if you can get OmniPage Pro for just $99.99, because the regular list price is $499. So maybe you want to get this email, but plausibly this makes you think, and you're saying offer and then dollars. Most emails that look like this, the kinds of words that occur in this are spammy words, right? And then another one here. So if you get this, if this is actually like Amazon.com and not something else, you probably want to know you're given some free certificate from Amazon so you can use it, right? Someone's giving you something. So the basic problem around here is that words are not enough to classify spam. So there are all sorts of other things you want to look at. So, for example, did it come from someone in your inbox? Is it your real friend sending you an email? If it is, for most of your friends, it's probably not spam. If did the links link to the right place, right? There are all these other things you can look at. And the way you'd figure that out is by seeing these cases and trying to figure out, okay, what is some feature which would justify this as being a good email versus a bad email? And so this is where kind of the creativity comes in, is because you've got to figure something out. But then you can test it, right? You can test it on held out data. So you can test your different, another thing you can use the held out data for is try different sets of features and figure out which feature set gets the best value on the held out data, right? That's a way of tuning things. So, here are just some examples. So, other kinds of features. Have you emailed the sender before? Yeah, if you're someone like Google, you can tell if the same email has been sent to 1,000 other people at the same time. That's probably a spam message or a mailing list. You've got to figure out which one is correct. Sometimes it says it's sent from someone, but it's actually sent from someone else. So if you could find that out, is the email all capital letters? That's maybe suspicious. Maybe you don't want to read that. Does it refer to your name? If they know your name, then you probably want to read that email, even if it's spam. So you can add all these features, and that's sort of the final piece of this. So, any questions so far about this feature stuff or any of the earlier Naïve-based things? All right, so next class, Peter will be here, and he'll talk about other kinds of classifiers which are not model-based, which are, not Naïve-based, and where it's particularly easy to add arbitrary sets of features. And so